Welcome to Lesson 3-3, Regression for Nonlinear Data. Our objective is, given a set of data, make a scatter plot, identify the type of function that could model the relationship between the variables, and use regression to find a particular equation that best fits the data. So, in the previous chapter, we had this line regression analysis, wherein we actually look for data that have a function, a regression analysis that could model a linear function. Now, the linear regression analysis does not apply to all situations, especially when we have a scatter plot that could most likely be about exponential or a power or logistically inclined. So these are the important matters in determining a regression for nonlinear data. Okay, so to begin with, we are given here a scatter plot of a data, okay? And this data, okay, is actually conveying the scatter plot of fish weight, y, versus the fish length, or x. And this is for 43 fish, okay? And going here, we have this scatter plot, and we have what do you call this? We have the data for the fish, and there are 43 fish in general, and the fish length as compared to the fish weight are varied. Now, for example, I caught a fish which measures 14.0 inches in length, and its weight is 5.5, let's say, pounds, okay? While I caught another fish, this time they have the same length, but it's a little bit heavier than the previous fish. And I've got the same fish, 15.1 inches, and it has 9.9 pounds in weight. And so I have 18.2 long fish, and it has 9.7 pounds of weight only. So as you can see, the data are scattered, okay? The fish length versus the fish weight are all scattered such that when they are plotted on an XY configuration, we have the length here on the x-axis, and we have the fish weight on the y-axis. And notice that the scattering of the plot give us a certain notation, which is either an exponential or a power function. Am I correct? Now, to understand the behavior of this scatter plot and to better judge which of the power function or the exponential function could best fit the model, we are going to look for the endpoint behavior. And what is this endpoint behavior? This endpoint behavior is the behavior of the scattering of data at the endpoint, meaning at the lower endpoint and at the upper endpoint. Okay? And if you are going to press the power regression in your graphics calculator, the power regression keys, remember that your grapher is capable, your grapher is capable of running the regression analysis. So in this case, we are choosing whether this scatter plot here is either power or exponential. But then we want to press the power regression keys first. I mean, we're trying to look if, this scatter plot could best fit the power regression line or the power regression model. So we press on the power regression keys, and the grapher will give us this formula, okay? y is equal to 0.0606 x raised to 1.7990. Now, are we convinced that this is indeed a power regression? So based on this point, the regression analysis here that we draw, okay, the regression curve for the power function, it fits perfectly the scattering of the data, meaning as you can see all of the points there cluster into the curve. So as you can see, the power regression is it's strong, okay? Its correlation is strong, okay, as compared to when we run the linear regression and the exponential regression. So here is the thing. If we're going to run a power regression, your grapher will compute for the correlation coefficient, and the correlation coefficient is 0.9669. Okay? Whereas if you run for a linear regression, just comparing, but you know, linear regression is the least of what we are choosing for this scattered data. Now the regression or the correlation coefficient is 0.9354, okay? Because it has a wrong endpoint behavior. Why? Look at the data here, okay? This is your linear. Let me choose the yellow line. This is your linear regression line, okay? You could see that most of the data are not clustering into the line, and it has a wrong endpoint behavior because at this point, you know, the lines or the data go there, okay? But the line goes like that here, right? So we have a wrong endpoint behavior. And we also have a weaker correlation. Look at the R. Your correlation coefficient is 0.9354, which is weaker than your power regression, which is 0.9669. Now we have another choice, and that choice is exponential regression. And as you can see, this points like an exponential line, okay? It seems like the data here, the points here, points to an exponential line. So let us trace that, okay? This is the line for the exponential curve. And look at your points. Some of the points are not even covered, right? Look at these points here. Some of them are far away from the curve, okay? And we also have a wrong endpoint behavior. Why? Because the exponential function or the exponential curve here shouldn't touch the x-axis, right? But look at these points here. They are near the x-axis, which means that at some point here, they are going to, if we have other data points here, they could compound, and they might, you know, touch the x-axis, right? And we also have a weaker correlation to the data because our R is 0.9557, which is less than this R here, okay? So the R here is less than here, and this R here is also less than. I mean, the R here is greater than here, okay? So therefore, the best fit nonlinear regression line or nonlinear function for this scattering of the points would then be the power regression. And as I have shown you, look at the when we use our linear function or our power function model, look at the points. they are clustering on the curve. So and we also have the right endpoint behavior, right? We totally got these points here, and especially at the endpoint, right? So that's how nonlinear data regression works. Okay, first we have to look for the endpoint behavior, and secondly we have to compute for the correlation coefficient R. Okay, those are the requirements. So the first is the endpoint behavior, and second is the R. If your R gives a better correlation coefficient, meaning it's a stronger coefficient, meaning it's higher, then that's the best fitting regression function for the graph. So our y hat here is equal to, just to clarify because it's not very clear here, 1.93 x minus 27.4. This is for the linear regression, and our r square is 0.88. Okay, while for the exponential regression we have y hat equals 4.29 1.06 raised to x, and our r is, or our r squared is 0.91. Okay, so the best fitting regression here is therefore the power regression. Okay,